Okay, so that started. Should I just start? I think everyone knows who I am. So without any further ado, we'll talk about the Riemann-Schottky problem. So probably, I think I thought about it for a while, and I think the best place to start for a discussion of this problem is, well, based on the background of everyone here, probably the Riemann mapping theorem. So what does the Riemann mapping theorem say? Anyone have any comments on that? Anyone know what the Riemann mapping theorem says? Or do I have to say because I'm the speaker? I'll say. So the Riemann mapping theorem tells us that if two domains in the plane are simply connected, plane domains, then they're conformally equivalent. Then there is map F from omega 1 to omega.
Fortunately, this is false.
What do you mean?
Well, unit disk and complex plane are not conformally equivalent. And
Okay, so I should take simply connected planes, plane domains, which are not all of C. Better? Okay, so good point, thanks. So omega 1 and omega 2 are simply connected plane domains, not all of C. Then there is conformal map F from omega 1 to omega 2, which is, well, conformal, invertible, and its inverse is also conformal. So I'll write it like that. F inverse is also conformal. So I'm going to call these domains conformal equivalents. So, and I'll write this. It's called conformal equivalents. And I'll draw a picture like it'll be helpful, but maybe it will be. So here's domain number 1, not all of C. Here's domain number 2, not all of C. And there is map between them, F. Okay. So hopefully that's a somewhat familiar result to everyone. If it's not, then, well, maybe we can discuss at some point. So furthermore, okay, I'll say it's that problem was too easy. It clearly wasn't, and Dima could probably talk your ear off on about how not so easy this problem ended up being. But for sake of discussion, say again.
I think there's some guy coming.
Oh yeah, I admitted it's Tony. Hey Tony.
Make me host, maybe.
Do what?
You can make me host.
Oh yeah, give me 1 second. I'll make you co-host just in case I lose my host status. Okay.
Cool.
I think it should be said now. So remapping theorem says to any two simply connected, not all of C plane domains are conformally equivalent. Let's up the ante just a little bit, and let's ask the same question for two doubly connected domains. Is the same true? So the picture is this. Here is doubly connected domain number 1. Here is doubly connected domain number 2. And the question is, does there exist map, conformal, inverse is also conformal, between the two domains? Does anyone know the answer? At least a couple of you do, but does anyone not know the answer? No problem. Well, if you don't know the answer, anyone have any guesses? Louis, what do you think?
I think no.
You think no? Okay, why not? It worked for simply connected domains. Why shouldn't it work for doubly connected?
Because it's not as nice.
Applied induction, it's true for any.
I thought there's a problem you always like to throw around, if I'm remembering right, is if two nonlinear are conformally equivalent if their ratios of their inner and outer radius are the same.
Exactly. So to reiterate what you just said, well, first, there's a nice fact that we can use that any doubly connected domain can be mapped onto an annulus, some annulus. And the key point here is that we don't have control over what the radii of this annulus are. So it can just be mapped onto some annulus conformally. So I'll call this map phi1. And same here. So the map phi1 and phi2 are both conformal, their inverses are also conformal, blah, blah, blah. But the key point is I don't have any control over the radii of these annulus. Annuli? Yeah, that just sounds weird, but maybe I should use different labels, but I think I will. So let's call this one maybe little r1 and big R1, and big R2 and little r2. And there's a nice theorem due to, well, I think it's Schottky, but depending on who you ask, the reference may be different. I think some people attribute it to Riemann. And it's actually a nice complex analysis exercise if you've never done it. So something to try at home. So it's a theorem due to, I'll attribute it to Schottky. That two annuli are conformally equivalent if and only if the ratio of the radii are equal. So if R1 over little r1 is equal to R2 over little r2, and you can think this just means that the one annulus is a dilation of the other. So in fact, this question, the answer to this question is false. The answer is no. In general, there does not exist a conformal map between the two doubly connected domains, but there is a characterizing factor. There's a one parameter family of what we can think of interpreting the result as follows. Two doubly connected domains are equivalent if and only if, well, this one parameter for each domain are equal. In other words, we can think of there being a one parameter family of doubly connected domains up to conformal equivalence. And I'll write that sentence on the next page. So our interpretation of this result is going to be the following. So up to conformal equivalence. There is a one parameter family of doubly connected domains. And this parameter, which here I called the ratio of the radii, I'll denote by tau, and it's called, well, the modulus, or the moduli, one of the moduli of this domain. In fact, in the case of the annulus, it's the only one. So tau is called the modulus of the domain. And you can think it's just a parameter that describes the kind of domain we're talking about. So let's go even a little bit further, because I think this was the cleanest introduction I could think of. So a further question: if I have G-connected domain, well, it probably just based on our previous analysis, probably won't be true that there will be conformal equivalence between two domains. So two G-connected domains. Let me draw the picture really quick. So here's, I'll just draw one G-connected domain for right now. So there are G holes in this domain, and they don't have to be circles. They can be, you know, like that, or maybe like that. So clearly these domains won't be equivalent because they have different numbers of holes. But suppose I have two G-connected domains. What number of parameters do you need, or how many parameters do I need to be able to say that these two domains are equivalent? Let me make it just so the picture matches. So 1, 2, 3 holes, 1, 2, 3 holes. How many parameters do I need? To characterize conformal equivalence. I'll state the question like that. Equivalent domains. So I think, well, at least Riemann knew the answer, but as usual, he didn't prove anything. And I think that, at least for plane domains, this problem was answered by probably Hilbert, yeah? So the answer comes from Hilbert, although I'm going to reference Kobe's answer just because it's a little easier to do the count, at least for me. So the answer, which is due to probably Hilbert, but I'm gonna reference Kobe. So the theorem says this: I can map any, say, triply connected domain or G-connected domain onto the disk with disk holes. So this is the unit disk and it has disk holes. And let's do a parameter count. So each disk hole has a center and a radius. Ooh, I gotta label them at least consistently. So this is R1, R2, and R3. And it turns out that two of these, well, disk with disk hole domains are equivalent if and only if up to a Mobius transformation, all of the radii of the disks have the same radii and all of the centers of the disk are the same positions, again, up to a Mobius transformation. So how many parameters are there? Well, there are 3 times the number of holes, real parameters. Where is the 3 coming from? Well, 2 from the coordinates of the center. That in a second. 2 coordinates from the position of the disk, and then 1 more from the radius. So that's a total of 3 times the number of holes. And then we have to mod out by Mobius transformation. So that's an overall subtraction of 6 more parameters. So we get rid of 6 parameters by, well, the action of this Mobius group. So this comes from counting the Mobius transformations. So well, in total there are 4 G-connected domains. G greater than or equal to 2, there are 3G minus 6 real parameters. That count as conformal moduli. So that characterize equivalence. Neat. So any questions about that, at least?
I'm unclear on how you got 6 for the Mobius transformations. How many parameters for each?
A Mobius transformation is specified by 3 complex coordinates or 3 complex numbers. Yeah. I specified. Yeah. Okay. So does that answer the question?
Yeah.
If you want to use fancy words, it's the Mobius group is 3 complex dimensional Lie group, but just Mobius transformation specified by 3 complex parameters is good enough. So if there are no other questions about that, then we'll keep going. So cool. That kind of just introduces this idea of moduli, which is sort of what I wanted to get at here. So the same sort of characterization is true for what we're going to eventually call Riemann surfaces. What is a Riemann surface? I'll always give a definition. So Riemann surface is a complex, I'll say 1D, and 1 means 1 complex dimension, complex manifold, with complex structure. And in particular, we're going to be interested in, an example immediately. These domains we just talked about are examples of Riemann surfaces. The local coordinate being on them, or the conformal structure coming from just a variable z on them. And in particular, we're going to be interested in what are called, or at least what are classically called, closed Riemann surfaces. Which, well, for normal people, is just called a compact surface with no boundary. Without boundary. And at least topologically, the things we're going to talk about are things that look like this. So I don't know if my picture is doing it justice, but that's supposed to be like a some sort of torus looking thing. So, maybe that's not a good place to draw, but this sort of picture. So these are the kinds of surfaces we want to talk about. And a point that I want to make really quickly is that we can construct from any of these plane domains a Riemann surface like this by gluing two copies of this domain together along the boundary and giving it good coordinates when you switch the other half by using the Schwartz function, essentially. But for right now, it's not so important. So similarly for closed Riemann surfaces, there's a count of the number of parameters. So the first kind of analog between what we were talking about before and what we're talking about here. The problem again is we want to talk about conformal equivalents of Riemann surfaces. And clearly two Riemann surfaces can only be equivalent if they have the same genus. So the characterizing factor here is not the number of holes, but well, a different kind of hole, the number of handles you can think in this surface. So in this case, this one has 4. Called the genus of the surface. I think everyone sort of, at least everyone here probably knows this already. So maybe I'll skip ahead a little bit. So Riemann surface has genus G, and clearly two Riemann surfaces can only be conformally equivalent if they have the same genus, because the map has to be continuous to start with, and its inverse also has to be continuous. So clearly two Riemann surfaces can only be conformally equivalent if they're, I think the plural of genus is genera. Correct me if I'm wrong. So we're interested in counting the dimension of the moduli space, the number of parameters, in other words, that we need to know in order to tell whether or not two surfaces of genus G are equivalent. My screen just went away, I think, and now I see Lewis. So 1 second. Back to Zoom. Where do I go? Meetings. This one. I don't want that. Share content. Screen. I still see only Lewis, but can anyone else see my screen right now? It died.
Before it died, it froze.
Okay. Can you see it now? Let me go back to this. I think it didn't work again. Let's try that one more time. Hold on. Stop share, share content. Where is screen? There it is. Okay, let's go very slowly back to Zoom or back to Teams. Is it back? Everyone can see? Okay, I see a couple of thumbs up, so I think we're good. So only if they're what we're talking about, conformal equivalents of Riemann surfaces, closed Riemann surfaces without boundary, and two are equivalent if only if they're, or can be equivalent only if their genera are equal. And what is the number of parameters we need to know whether or not two Riemann surfaces are equivalent? Well, number of parameters. I'm going to write as a function of the genus is equal to, well, there are none if the genus is equal to 0. So there's only one simply connected closed Riemann surface, and it's the Riemann sphere. So I'm just going to state the result so we can get on to other things. In the case of genus 1, there is one complex parameter. So the dimension is going to be number of, we had the word complex up here. And finally, so these are all tori, you can think. And finally, in the higher genus case, it's a little bit non-trivial, but it's 3g minus 3, g greater than or equal to 2. So this is for higher genus Riemann surfaces. And this result was known to, I think, Riemann, although again, he didn't prove it. So in the spirit of Riemann, we won't either, is how I'll say it. But this is a nice fact that we're going to take for granted later on. So it's necessary, at least for the statement of the problem that we're going to make. And hopefully, at least just based on time, today we'll at least be able to come to the statement of the problem. So in order to state this Riemann-Schottky problem, probably the cleanest way to state it is to actually state it first for plane domains and then come back and try to state it or build the necessary technology to state it for Riemann surfaces. I might just skip because I think, well, I don't know. How does everyone feel? Would you rather see it for plane domains first, or do you want me to just skip ahead and build the necessary technology to do in Riemann surfaces? Which sounds more appealing?
For me, do it for the plane domain, but it's your talk. You can do
Okay,
whatever you
so
want.
Lewis says plane domains. Anyone else have any comments? Otherwise, I'll just do it for plane domains, and then we'll at least come back and build the tools to do it for Riemann surfaces. So kind of an important question, or relevant to describing this.
When you because you are talking about compact Riemann surfaces, and now you are talking about domains, so you are talking about doubles, Schottky doubles, right? Because plane domains are not compact.
No, sure, and we even know there's a discrepancy, yeah? Oh, well, maybe, I'm not sure. So that's always a point that I've been kind of unclear about. Just because you can double domain, you can build a Riemann surface out of it, but it's already a Riemann surface with, well, non-trivial automorphism group. So is it really all Riemann surfaces? But it's for our purposes, the plane domain thing is just a good analogy. That's very down to earth in comparison. And most of the kind of theorems we're going to state for plane domains end up being the same theorems that we're going to state for Riemann surfaces. So that's the only reason I would go down this route. Does that sort of answer? I don't know if I answered the question at all. I think I just said something else, but does that answer the question? Okay. So we'll start with I'll label this one Riemann-Schottky problem. For plane domains. Because it's actually, well, relatively easy to state for plane domains. So one of the points of interest, first of all. So we're interested in kind of getting a good descriptor of, well, what these parameters look like in the case of, well, Riemann surfaces. So in the case of what the space of these domains look like is what I want to say. So what the parameter space of these domains looks like as an object. And this space, by the way, has a name. It's called the moduli space. So for plane domains, we already had kind of a good set of local coordinates, which I drew here. They were the centers of these disks and their radii. So that's one descriptor of this moduli space that we could use. But another descriptor we're going to use is in terms of these things called period matrices, which it's a theorem due to Torelli. Well, actually, I don't think it's even due to Torelli. I think he didn't prove it, or he proved it wrong. And it wasn't corrected until sometime later. Do you know when it was corrected, Dima? The actual Torelli's theorem?
It was corrected, the first correct proof. I mean, he thought he proved it, but he didn't. In the 1920s, with this Italian school of algebraic geometers. The first correct proof, I think, was Andriotti Meyer in 1965 or 66.
Okay. So a good historical note there. The theorem we're going to at least mention wasn't proven for quite a while. So it's essentially, for our purpose, is going to be another description of this moduli space in terms of, well, some number of parameters. And these parameters are going to be called periods of this Riemann surface. So some characterizers of Riemann surfaces of genus G. That's not the pen. Or I'm sorry, plane domains. We're talking about plane domains first. So here is a plane domain. And we're going to associate some differentials to this domain. So to each plane domain, T connected, we're going to associate a family of G differentials. And how are these differentials defined? Well, they're defined in terms of harmonic measures. So what I'm going to do, let me label the boundary components. This is going to be, well, here we only have 1, 2, 3, 4. So I'm going to label this gamma. Well, I'll label it gamma 3 maybe. I don't know. Maybe I'll label it gamma 0. gamma 1, gamma 2, gamma 3. And I'm going to define some functions for each of these boundary components. So I have the boundary components labeled now. Gamma 0 will always be the outer boundary component. And consider the solution to the following Dirichlet problem. So omega j is harmonic in sign, and on the boundary is equal to delta jk. And this is, there are going to be n of them, or to g, I guess. So we consider the harmonic function, and again, just to avoid technicalities, we're going to assume for right now that our domains are nice, so that this problem has a solution, blah, blah, blah. So what do each of these solutions look like? Well, they're 1 on this boundary component, 0 on all the others. So we have 1 here, 0, 0, 0 here. So they're called harmonic measures of the boundary components. And we're going to build differentials out of them. So how do we build differentials out of them? Well, I'm going to define a to k, or a to, let's keep variables the same, a to j to be d omega j, dn, ds. ds is the arc length measure on the boundary. So ds equals boundary omega. So this domain is going to be for us omega. So right. So it's a, I'll say, relatively easy fact to verify that these differentials are linearly independent. And furthermore,
which normal you are, I mean, it doesn't matter very much, but
no, I'll take outer normal. I like outer normal better, but again, it doesn't matter. So let's specify outer normal. Although if we're sticking with the notation to your class, probably we should do inner. But it doesn't matter. So it's the facts about these differentials. They are linearly independent. At each point, meaning, well, if I consider the Wronskian of them, of the coefficients, you get something non-vanishing at every point. And we're going to define a matrix associated to now this domain. So let me write over here. So the period matrix. So I'll denote it by little pi on jk, and has components jk, and it's going to be defined as integral over, I guess it doesn't matter, gamma j, eta, did I call them etas? I did, eta k. So I integrate this differential, I'll write it out explicitly, d omega k dn ds, over the jth boundary component. And this number I get at the end is going to be called the, well, pi j kth component of the period matrix. So this matrix here is called the period matrix. And it has some, well, easily verifiable properties. If you know Green's theorem, you can readily verify them. So I'll write by Green's theorem. Pi jk is a symmetric matrix, and it's positive definite. Okay, cool. And the theorem that we were mentioning before, which is due to Torelli, well, not due to Torelli, I guess, but what is called Torelli's theorem, is that I'll state it like this: the conformal class of a domain omega can be recovered from its period matrix. So in other words, if I'm given this matrix and I don't know the domain, I can reconstruct the domain uniquely up to conformal equivalents, which is a nice property. So in some sense, it tells me that, well, the space of these matrices, well, this matrix kind of has all the information I need to know about the plane domain. So in human language, The period matrix we're going to denote by pi jk. We're denoted by pi of omega. Encodes all relevant information about the conformal equivalence class of omega. And so I can think, well, my first kind of wishful thinking thought is that, well, maybe I can treat the space of these matrices as, well, the moduli space of these surfaces, or these plane domains. So I can actually, instead of working with, well, these weird coordinates where I had, where was it, a couple pages ago here, these radii and these centers as the coordinates of this moduli space, maybe I can instead work with, well, just the coefficients of this matrix and treat them as parameters in the moduli space. But there's an immediate issue. Well, the dimension of the space of these matrices. So let's consider, let me state it like this. So the set of all such matrices. So consider the set of all matrices such that one, well, they're symmetric. And two, well, they're positive definite. And in this case, I think they're just positive definite. You need to require the imaginary part is positive definite, which is going to change when we talk about complex Riemann surfaces, but regardless. So consider the set of all matrices with these two properties. Well, by an easy count, if they're G by G matrices, so set of all G by G matrices, the positive definite condition doesn't reduce the number of parameters at all. It just kind of picks a sub-slice of the set of G by G matrices, but the symmetric condition does. So how many parameters are there in a G by G symmetric matrix? 3 parameters. Well, there are G on the diagonal. And then, well, G minus 1 more up here. So there are G here, and G minus 1 over 2 more over here. And anything on the lower diagonal is just repeated. So there are a total of, so the dimension of the space of these matrices, real dimension. I'll call this set SG for Siegel matrices, is G plus G minus 1 over 2, which is what we can add. What is it? So I have 2G over 2 plus G squared minus G over 2, which is G squared plus G over 2, which is G plus 1 over 2. Which we remark, which in general is not equal to, well, this parameter count we got before, so 3G minus 6, except for maybe in some special cases. So these two numbers are different. So in other words, the set of matrices of this type, which we're going to call Siegel matrices here, we'll have a different name later. But the set of these matrices is a lot bigger than the set of plane domains. And so, well, what we're actually doing when we're looking at just these plane domains is carving out some weird subset of the space of matrices of this form. A submanifold even, maybe we would like to know, actually. So the question is, and this is the Riemann-Schottky problem. So here is the problem. Finally, among all such matrices, SG, which are the period matrices of G-connected domains. So this is the problem, which was posed by Riemann-Schottky, so on and so forth. Is, again, there's this discrepancy in the dimension of the space of both these matrices versus the space of actual, well, plane domains of genus G. And we would like to know, well, among all such matrices, which ones are actually the period matrices of Riemann surfaces, and not just, well, some random matrix. No relation. So is the problem clear? Is it clean cut? Does everyone understand sort of what it's saying? If not, I can reiterate or talk about something else that maybe will make it more clear. I don't know. Any questions? If not, then we're going to move on to, well, the same problem for Riemann surfaces, which is we're going to build a little bit of technology for. And hopefully, if not this time, then next time, what we'll try to do is actually answer this problem for Riemann surfaces. So the characterizing factor, which tells us whether or not such a matrix is actually the period matrix of a Riemann surface. So if there are no questions, then I'll go on and talk about the same problem. I'll call this 2. For Riemann surfaces. Closed Riemann surfaces. So there is an analogous problem for closed Riemann surfaces, and essentially the statement is going to be exactly the same. We're just going to dress it up a little bit to make it look a little bit fancier so that it kind of fits into the context of well, algebraic geometry, and also into the context of the place where this problem actually is answered, which is integrable systems. So actually, by the way, did anyone take Anna's class when she taught the algebraic curves over finite fields? I don't know if Lena, did you take it or no? Maybe not.
No.
Okay, so no one took it, so I have to start from scratch. Right, so we're going to describe this problem first for Riemann surfaces, and then hopefully we'll answer the problem, if not this time, then next time. So some preliminary notions for Riemann surfaces. Here is a Riemann surface. And we're going to construct a couple canonical objects on this Riemann surface. The first thing we're going to construct is a basis of, well, cycles. So anyone that's taken probably, is it topology 1 or topology 2, which you do this in? Anyone that's taken a topology course knows that on a surface of genus G, the first homology group has dimension 2G, and it's formed as a basis of what we can even pick a normalized basis of cycles on the surface, which is what we're going to do now. So here is, I'll call these A cycles. This is A1 and A2. And then we have B cycles as well, which go around the other way, like this. And it's clear enough from the picture that, well, how many cycles are there in total? There will be, well, linearly independent cycles. There will be 2G linearly independent cycles, and any other cycle I can create as a linear combination of these 2G that I just drew. In this case, there's only 4. So we pick a canonical homology basis. So AIs, BIs, I equals 1 to G, such that they're intersection matrix. So I'll write it like this. And this dot means intersection, number of intersections. Sections, AI.aj is 0. AI.bj is delta ij. They intersect at 1 point, this one here. And finally, the B cycles don't intersect either. So this is our canonical basis of for the homology group on this space. And for all intents and purposes, this is the analog from before of just the boundary components of this domain. So the thing we just, or the basis we just constructed is the analog of these things. And it's just picking a canonical one. Okay, so what else do we need an analogy for? We need an analogy for, these things. Well, these things in particular, called the, well, holomorphic differentials. So I'll state it as fact, and it's actually a good exercise to prove if you've never done it before, and you know at least a little bit about Riemann surfaces. If you don't, then maybe don't attempt. But a fact is that there are G linearly independent. Independent. I don't know why my spelling gets bad when I'm writing on a board. Independent. Usually my spelling's not this bad. Independent. That looks right. Holomorphic one forms. And before anyone catches me, I'll say something. Actually, no, it's still technically valid of genus G. So notice that in the case of genus 0, there are none, which, well, anyone I think here can readily verify that there are no holomorphic one forms on the Riemann sphere. Genus 1 case, DZ is the one, and there's no other ones. And then higher genus ones, well, there's an explicit construction that kind of goes off two facts. One is you can construct one forms which are non-vanishing on each cycle and vanish on all other cycles. And then second, you can make them holomorphic or harmonic, and then you can combine them in ways that they're holomorphic. So that's sort of where this fact comes from. And of course, it doesn't really bother us that in the case of genus G, there are none because, well, or sorry, in the case of genus 0, there are none because we're not going to really care too much about genus 0 in this case because it's just like Remapping Theorem. There are no non-trivial examples of, well, conformal equivalence classes. So for genus G, genus 0, we don't care so much that there are none because we're not going to deal with that case at all. So from now on, G is greater than or equal to 1. And sometimes I'll even take G greater than 2 just for, there's even a distinction. Genus 1 is even sort of a special case, but unless I specify, it will always be genus G greater than 1. Right. So just like we had a canonical normalization for, well, the cycles up here, there is a canonical normalization for these linearly dependent holomorphic one forms, which I'll denote like I did before by A to J's. So this is a basis. And it's the canonical choice, or one of the canonical choices, is chosen so that the cycles have special properties. So I have, well, G things. So I can specify G things to, well, create a unique basis. And the G things I specify for each of them is going to be that the A cycles of these. So if I integrate the jth differential over the ith cycle, I should get 1 if I is equal to j and 0 otherwise. So the A to j's are chosen in this way so that this condition is satisfied. And it's a normalization. It's not necessary really for anything except for convenience of notation later, but it will be convenient. Okay. Do I need to explain anything else here? I don't know. I mean, we could go into depth with this, but we'll be here probably all day. So is it sort of clear what's being spoken about? There is canonical homology basis. There is canonical basis also of cycles, just like there was before.
I'm sorry, if people didn't see it, I mean, I think the example of genus 1 is where you can write down the differential explicitly.
Ah, sure. So genus 1, all right. So genus 1 case. What does a genus 1 Riemann surface look like? Well, it's a torus, and actually it's a good point. So maybe I should talk about that. How are we going to represent a torus? Well, take a lattice in the plane. So omega 1 and omega 2. I don't think I've used omega yet, have I? Are linearly independent complex numbers. And I consider this lattice of points generated by them. So maybe this is omega 1, that's omega 2. And, you know, I tile the plane with these lattice vectors. Well, it's not drawn too great, but I think you get the point. So it should look like what? This, that, so on and so forth. I quotient the complex plane as a complex manifold and as a group by this lattice. So in other words, I identify points. Z is equivalent to W if Z minus W is in the lattice. And what I get at the end is a torus. Why? Well, if I look at this fundamental parallelogram that I've drawn, one of these cells, well, all the points on this upper edge are identified with all the points on this lower edge. And all of the points on this left edge are all identified with the points on this right edge. So what we have, topologically speaking, at least, I can glue them together, is a torus. And what is a good holomorphic differential on it? Well, just dz. Dz is first of all well defined on this quotient, because when I pass the quotient dz plus lambda for any complex number lambda, it's the same thing as dz. So it's well defined on the quotient space. And furthermore, it's holomorphic because dz doesn't have any problems in this rectangle. So there's your one linearly independent holomorphic one form. The normalization is kind of dumb here. We just divide by a constant so that we get 1 when we integrate over the A cycle, whatever I happen to label the A cycle. But in any case, it's a good example, and it's, well, relevant to what we're going to talk about soon. Okay. So I think it's worth introducing this map. Let me think about this, what I want to do. Maybe we'll do it in a second. So where does this period matrix come from? Well, if I look at now the B cycles, because I saw that I could normalize these differentials with the A cycles like this, and what's left over are the B cycles. So our period matrix now is going to be pi ij. This is our new period matrix, and it satisfies well, similar properties to the period matrix we wrote down before. The only difference now being is that the entries are complex. So property number 1 it satisfies is that it's symmetric. And 2, it satisfies that its imaginary part is actually positive definite. So properties of pi. So it has these 2 properties. And again, if you consider the set of all matrices, so let's recall some facts that we had before. So the space of matrices with these 2 properties I call SG. And now it's dimension over C and not R this time. So its dimension over C is the same as what I wrote before, which is GG plus 1 over 2. But on the other hand, what? Well, on the other hand, at least for genus G greater than or equal to 2, this is not equal to 3G minus 3 in general. And so the Riemann-Schottky problem asks the same question. Among all such matrices, which are the period matrices of Riemann surfaces? Because again, we have, maybe I didn't say explicitly, but it's implied. So Torelli's theorem still holds. So this matrix is enough to actually recover the conformal structure of the Riemann surface we were talking about originally. And well, they embed nicely into the space of these matrices. But of course, the dimension of the space of these matrices is a lot bigger than the set of these parameters. And so the question is, among all such matrices, which are the period matrices of Riemann surfaces? And that question, well, just because we're running out of time, I'll at least state the answer. It was in the abstract. The answer is, so pi is the period matrix of a Riemann surface, and this is pi coming from SG, is the period matrix of a Riemann surface if and only if its corresponding theta function, and I'll hopefully explain what that is in the last few minutes. And I'll say defines, but it's defined in a little bit convoluted way. Defines what a so-called tau function for this KP hierarchy. And well, the forwards direction of this, well, the backwards direction of this is due to Krichever, who's a student of Novikov. So we go Krichever. And the full proof, which is the forwards direction, is due to, and this is, I think, 87. No, it's 76, and this is 87. Or this is 86. Maybe this is 77. I forget. I'll put a question mark here. It's mid 70s for that one, but this one's definitely 86. And this is Shiota. So this guy was doing integrable systems, and this guy I think is actually an algebraic geometer. And hopefully next time I'll actually be able to explain to you, well, at least a sketch of this proof. So the equivalence of the two, the forwards and backwards directions. And really the interesting direction is this one. This one, it was just only a matter of time before people discovered that it was actually true. But this is really the interesting direction because it kind of ties, it really illustrates the connection between integrable systems and algebraic geometry. Some words need to be explained now. The first word that needs to be explained is theta function. So I think I can avoid entirely talking about the Hubble-Jacobi, maybe. We'll see. So back to Riemann surfaces. No, I think it'll be necessary. So it's of interest to try to write down functions on Riemann surfaces like this. So we want to write down functions on these Riemann surfaces with prescribed singularities. So this is a typical problem. I mean, I have a manifold, and I want to write down a function with certain properties on it. So since it's like a complex analytic manifold, probably the thing I want to talk about is some sort of meromorphic function with prescribed zeros and prescribed poles. You can think it's the analog of a rational function for right now. So the kind of method that was eventually developed to do this, in it's not really maybe the most practical method of doing it, but it's certainly a method that is as general as it gets, is due to Hubble and Jacobi. And it involves, well, this thing called the Hubble-Jacobi map and theta functions. So I'll explain each briefly. So first of all, what is this Hubble-Jacobi map? Well, the Hubble-Jacobi map is a map from a Riemann surface sigma of genus G into a complex torus. So I'll write it like this: C modulo some lattice, CG modulo some lattice. So I is all lattice. And how is it defined? Well, I take a point on my Riemann surface. Let me draw the picture. Here are some holes. I mark a point, P star, and I consider the problem of integrating from P star to a point P on the surface. And to this point P, I associate the vector integration from P star to P of eta 1, integration from P star to P of eta 2, so on and so forth. So this map is seemingly ill-defined because, of course, I could, well, integration from here to here maybe is different from integration from there to there. Well, it's not unless I go around a cycle first and then I come and hit this point. So integration is seemingly defined only up to cycles. But the nice fact is that, well, so integration is defined only up to cycles. But how do I remedy that? Well, I just quotient out by all of the cycles because they all differ by integer multiples of a number of either periods or integers because of how I normalize these differentials. So they differ by either integer multiples of these numbers or just integers. And so if I just quotient by the lattice formed by those things, I get a torus. And this thing here is well defined on that torus. And this object is called the Jacobian of the Riemann surface. So this thing here is called the Jacobian of sigma. And in this new language, essentially what is being said, so what Torelli's theorem says is that a Riemann surface is characterized by its Jacobian. And I have one more sentence I'm going to say, and then I'll be done for the day. Characterized So now that we have this nice embedding of, and I'll call this map maybe Z for fun. Now that I have this nice embedding of, well, the Riemann surface into this torus, I can essentially just look for functions on this torus and then try to write down functions on this torus using this map. So if f is a function on the torus, modulo gamma, into C, well, I just take the map from the Riemann surface. So this Abel-Jacobian map, and now this is a map from the Riemann surface into, well, C. So any function I want to define, I can kind of build in this way. I first define this Abel-Jacobian map, and then I can just treat functions on this surface. And the canonical function I can define on this torus are these things called theta functions. So a theta function associated with the surface, so pi is the period matrix, is defined to be the sum n in ZG, and depends on normalization. I might change it next time. E to the pi I, and this is inner product I'm writing now. N pi n plus I think I want 2 pi I n. Let's make this z dot z. So maybe I should keep it because it's not right. Inner product of that. So this is a function defined on the surface. It has several periodicity properties, which we'll talk about next time. And this is the sort of thing that we're going to kind of build off of. So any questions? See you later, Lena.
Shouldn't you say why the series converges?
Yeah, sure. So why does it converge? Well, it's because of this matrix being positive definite, yeah? Or its imaginary part being positive definite. Actually, maybe if I normalize it like that, it won't be, yeah? So maybe I want, no, this is good. So it converges because of that property. So if I take absolute value and squish everything in, then it converges as it should. So it's because of the positive definiteness of this matrix. And
It's exponential decay. Yeah.
Right. So we kind of rushed at the end a little bit, so we'll discuss a little bit more about this next time. Because this is sort of the object that we're going to kind of build things out of from the integrable systems perspective. Kind of the idea, at least for the beginning. Where did I draw the last page? It's going to be this direction. And we're going to talk at the beginning a little bit about integral systems and forget this whole story about the Riemann-Schottky problem. We're going to construct explicitly solutions from essentially the following data: a Riemann surface, a special mark point, and a positive divisor, just a set of G points on this Riemann surface in a non-special position. Given that set of data, we can actually construct a solution to this so-called KP equation and solutions to the whole KP hierarchy. And then from that, we kind of noticed that, well, this construction is pretty general. And, well, we're going to pretend that we're Novikov and actually conjecture that the opposite direction also holds. So if I have such a solution, I can actually go backwards and construct the corresponding Riemann surface, which is very much in the spirit of this Birchnall-Chondy theory, if you've ever heard of that.
Theory?
Birchnall-Chondy, I'll write it at the bottom. So commuting subrings of differential operators. It's like a deformation of this in some sense, and people have kind of termed, well, Shiota's construction, Birchnall-Chondy Krichever theory. So that's sort of the flavor of what we're going to talk about next time, and we'll see how far we get. But yeah, so any other questions?
One comment is that to show them how difficult this problem is. I mean, you know, that there are not plenty of matrices which are not period matrices because there are this very non-trivial relations period matrices satisfy called Riemann bilineal relations.
Yeah.
Which the other thing is like with all this solution, can you tell which matrix let's say,
it is?
Yeah, 2 by 2 matrix, symmetric matrix, is a matrix of a hyperelliptic surface.
So can you tell what kind of surface you have? In
Well,
principle,
hyperelliptic because it's a pretzel. So
sure. So in principle, yes. In practice, I'd have to think about it. Probably not, I would say, but in principle, yes. Because you know the conformal class of the Riemann surface. So in principle, you could reconstruct.
yeah, no, in principle, I understand that this theorem, which I don't understand either, answers this question. But when I was thinking about it, I mostly was thinking about Torelli theorem for planar domains. I wanted to get the conformal. I mean, for planar domains, you want to get a conformal from this period matrix. You want to cook up a conformal map into canonical domain. And unfortunately, it's okay to do it for annuli, and already for triply connected domains, there is a problem, which
Well, I had two more things I wanted to mention. So one was to address something you said just now. So the corresponding theorem for plane domains probably exists. It's just what kind of Riemann surface. So if you have Riemann surface, which is Schottky double of some domain, so you kind of push this problem up into the space of Riemann surfaces and ask what sort of solutions to KP you end up with. I suspect it's probably the kind Fedong wants, which are that they're real when T is real.
well, there was a paper by Schiffer and Howley in 1966 in ACTA, which sort of claimed the solution of this problem, but again, it's very indirect.
Yeah, so there's also, that's another kind of partial solution, which is also connected to all of this. It's called phase trisecant identity. I don't know if that was the one. But there's a similar kind of characterization.
No,
So
I think the title of Schiffer-Howley was exactly
that, yeah.
Schottky doubles of the planar domains.
Okay. So just another comment, so I'm not hiding anything from you all. There is actually sort of another solution, but it's the same solution to this problem. So it turns out that theta functions coming from Riemann surfaces, so from Jacobian varieties, satisfy a certain identity called phase trisecant identity, which a generic theta function will not. But it's essentially, it turns out to be exactly the bilinear equation that the tau function satisfies, it turns out. So it's not so surprising from that point of view. But
I don't know if you know this. When I was interested in this, it just sort of barely came out. There is a book by John Fay, who was an Alphorus student, theta function. Actually, somebody just today pointed out to me that it's living this year, its 50th anniversary since it was published. There was also another guy who came from Washington University in St. Louis, who now is in Sweden, Dennis Heichel. He wrote a book on theta functions. I don't know if you.
I don't know.
He started with multiply connected domains, and then he sort of dived into Riemann surfaces and theta functions and Torelli. Well, I don't think he never came to the surface again. I mean, he did fantastic work there, but he never did any classical complex analysis afterward. But he also he has a book on theta functions. They came out about the same in the mid-70s.
Yeah. Well, that was another idea I kind of wanted to sell, is that, well, the theory of integrable systems and algebraic geometry are kind of intimately related. And this is sort of one of the first like concrete connections that was actually made between the two. Was this another one, which came, I think, in the 90s, was due to, what's his name? Kontsevich, who showed that intersection numbers on this moduli space can be written in terms of, well, certain solutions to K or KDV. So another connection to integral systems.
Who was that?
Kontsevich, Maxim Kontsevich.
Oh, Kontsevich.
Yeah.
Well, I mean, again, it sort of goes back to Jacobi, who proved that ellipsoids are the only integrable systems known to mankind. That's actually how he got into elliptic functions, which is data functions. Anyways,
No, there's a pretty history of the whole thing, which is kind of neat.
yeah, well, yeah, I mean, this subject has been around for a
Yeah.
while.
So
Great.
that's
So
all I can say for right now.
Next week you can continue, right?
Yeah, I'll hopefully conclude too.
Oh,
Good luck.
Yeah, we'll see. So any other
Okay.
questions? Otherwise, I'm going to stop recording and be done. And I don't hear anyone, so I'm going to stop.